Okay, great. Well, I'm very disappointed in all of you, or the 28 of you or whatever, who haven't tried the notebook. But we should get it sorted out over tea, don't worry about it. So today's going to be a little bit different from the last 3 days, not least because it's machine learning, not statistics. The way I lecture is quite interactive, so I'm going to make Guillaume work quite hard with the microphone, and I'm going to expect a lot of interaction from you guys, answering questions and asking questions. So if you have a question and you think it's a stupid question, ask it anyway, because the chances are so high that the people around you have the same question. So be brave, do your friends a favor, and ask. So who am I? I'm Michelle Lochner. I'm South African. I've got a joint position between the African Institute for Mathematical Sciences and the Square Kilometre Array. And I've also got my foot in the door with UCL as well, in London. And I'm a cosmologist, but I have pretty broad interests. So I do a lot of kind of developing new techniques to solve problems in astronomy and cosmology. So I've done things from supernova cosmology to coming up with new statistical methods for radio interferometry, working quite close to raw data. So I do a lot of statistics, but I also do a lot of machine learning. That's what I'm going to talk to you about today. What you probably don't know about me, and probably what I think even the organizers probably don't know, is this is not my first time here at ESA. In 2009, as part of the International Year of Astronomy, ESA ran this international competition called Be an Integral Astronomer. And I was in my 3rd year at university, and I came across this competition, and I obviously decided to take part, and it was the first time I had ever got anywhere near real astronomical data, because it was real data from Integral. It was the first time I'd ever written a scientific report, and it was the first time that I'd used Python for data analysis. So there were a lot of firsts for me. And I have to say, at that point, I was studying physics, I liked physics, and I was heavily influenced by the SKA, I have to say, influenced my career a lot. But this was the point when I decided I wanted to be an astronomer, because I'd actually done this. I'd done some research, some real research. And I would say that this was a key moment for making me decide to carry on, to be an astronomer. And here I am, 8 years later, back at ESA. So the first prize was a visit to this very place, and there's me in one of the other buildings, and in front of the model of Integral, I think. And you should recognize this thing. So yeah, I just thought this was quite a nice thing that you guys probably didn't know about.
Thank you very much for saying this. I mean, I'll just add, maybe we should just give a round of applause, because that's quite great. I mean, we were organizing this competition in order to increase kind of awareness about Integral. I'm an integral scientist. I've been working on Integral for 16 years now. PhD in ISOC, so I think it's really great that this was such a turning point for you. So I'm very happy about that.
Yeah, it really was. I didn't carry on working with integral data. I went into cosmology, but it was the first astronomical data I ever looked at, and I thought it was really weird. Okay, anyway, so that was just an aside. Today, you should all have hopefully seen this link come up again and again and again. Please go to it if you haven't, and clone this repository, or if you don't know how to use GitHub, there's a little download zip button, so you can download everything that you need there. And we'll be using Python today. I'm a very strong Python user. A lot of this stuff you can also do in R, so if you like R, that's also a great place to do some machine learning. But Python's probably the most commonly used language in astronomy. Maybe that could be debated. One of the most commonly used languages in astronomy. It's definitely the most commonly used in the machine learning community. There's a great package called scikit-learn, which will do everything you need for machine learning, for basic machine learning. And it's really great, and it's really easy to use. Along the way, along the slides, you'll see things that are in this kind of font. You know, we know how great Python is from Python import solution, done. So you'll see this kind of text on the slides. Whatever I'm talking about, whatever concept in machine learning, if it's an algorithm or some kind of functionality you need, this will be a clue as to where to find it in scikit-learn. right? So you should have, there is a version of these slides, there's like a censored version of these slides in the repository if you want to go through them. And so those links to those libraries, that's what you want to be searching for when you actually get to doing the tutorial, so that you're not just Googling from scratch. So just keep an eye out for these. I will tell you where to look. All right, so let's get started. What is machine learning? This is also a pretty debatable question, actually. My interpretation of what machine learning is it's a way of automatically building up a model that maps inputs to outputs for supervised learning, right? So you have some kind of way of automatically building the model. You know, so in Bayesian statistics up till now, we've most of the time been talking about you already have a model for what's going on. You have a model for your data and you fit the parameters. In this case, you say, I don't really know. I don't really know how to get from inputs to outputs, and machine learning will figure out a way to do it for you, right? So simply put, I think that's what machine learning is. So when should you use it? You can use it for data exploration. So this is when you're doing unsupervised learning, looking for patterns in your data. This can be quite powerful. More or less, when we talk about unsupervised learning, we're talking about clustering. So are there clusters in my data? So this is, I think these are Wikipedia articles, actually, in some sort of feature space. And it vaguely forms some clusters around topics, but obviously it's quite complicated, so there's a lot of overlap. And you can see here there's a very clean cluster, and you might look at that and say, okay, what's that data? What's different about that data? So it can help you with data exploration. But I think the real power of machine learning and where it's most commonly used is what's called supervised learning. So you might use machine learning when you don't have a good model, when the data is so complex that it's very difficult for you to build up a model to use statistics for. You might also use machine learning when you're lazy. I mean, I'm too lazy to classify 10 million transient alerts from LSST every night. So I'll use machine learning for that. I really like this because I hate cooking. I really hate cooking. And this is a pair of robot arms that will watch you cook, and then if you put all the ingredients in front of it, it can replicate a meal for you, right? And so this is amazing. As soon as this becomes even remotely affordable, I would like to get those. Sorry?
Synthetic image.
It's a synthetic image. Well, this is a prototype, yeah. All right, so time for you guys to talk and for me to listen. If you'd done your very, very easy questions, your very easy short pre-lesson readings, you would have found this question. Why has machine learning, which has been around for around 50 years, only recently become so popular? And really the word so is in there. I mean, there's a very strong community of people who've been using machine learning for many years, but its popularity has increased exponentially recently. Why? Hands up. Anyone got any ideas? So Guillaume is very religious about hands. So let's do hands. There's a hand at the back. There's two hands at the back. Okay, fine.
Computing power.
Computing power. What else? There's one there.
Same
Google,
answer.
Google.
Sorry?
Google.
Google.
Big data.
Good. Data size. Yeah. I like that. So for me, that's actually the biggest reason. Computing power helps, and especially for deep learning, it helps. But the biggest thing is that a huge amount of data has become available. And the biggest thing is companies like Google, Amazon, Facebook are realizing the commercial value of this data. So a lot of machine learning research is actually being driven commercially, right? That's where a lot of the cutting edge research is happening, is companies like DeepMind, owned by Google, for commercial benefit. So I personally think it's the availability of data that makes it so popular. Here's another question. What's an example of where machine learning is being used in your everyday life? Sort of at the back.
Phone.
On your phone? Like
Yeah.
what?
Like recently in images.
Images? Okay, what else? Back. If you shout it out, I'll just repeat it. Voice recognition, yeah? And you put anything in Google, and you search for anything in Google. What else? Shopping on Amazon. Not very good sometimes, right? The recommendations. People have bought this stuffed frog. What? Yeah? Social media.
Netflix.
Netflix. Netflix uses a lot of machine learning. Spam filtering. Lots of machine learning there. Anyone else? When you go to work. Are you the machine? So yeah, there's a lot of stuff. My personal favorite is music streaming. So I use Google Play Music, and it's amazing. I've really trained it well. Like I can just say, play me music, and it plays me a whole lot of stuff that I like that I've never heard before. And especially if you know something about machine learning and you know that you got to train it, give it lots of training data. So I've done that, and it works beautifully.
You're still doing mistakes.
Really? Then, well, maybe your music tastes are too eclectic. All right, so let's do some definitions. Right? Machine learning is quite nice. There's not too much jargon. There's not too much terminology. There's a few terms that we need to know, and then we can carry on. You always start with your data. We're always very data-driven in machine learning. So you've got to start with some set of data. What you would usually do in traditional machine learning is feature extraction. Why? Generally, if you give an algorithm just a bunch of raw data, like if you gave it some raw images, some pixel values of images, or you gave it housing prices or whatever, or any kind of raw data, it's usually very difficult for the algorithm to interpret it, right? Your classification is not likely to be very good, or regression, or whatever you want to do. What you have to do is extract features from your data that the algorithm can actually use. So for instance, like Netflix, building a recommendation engine, right? You're not going to pass it a raw movie. You're going to pass it things like, what's the genre of the movie? What was the amount of money spent on the movie? Is it classified as a blockbuster movie? Is it, what language is it in? What actors are in it? These are features that you would take, this information about your data, that you can pass to the algorithm, and it could build a recommendation engine. So here's an example where, and I will just say that deep learning breaks this. You don't actually need to do feature extraction for deep learning, and we'll get to that much later. So for instance, if you had an image of a fingerprint, and now this is one of the oldest uses of machine learning. Fingerprint scanners are now very good. You might extract these things called minutia points, which are specific points in a fingerprint that are known to be unique identifiers. A combination of them is known to be a unique identifier. You might build a map out of these features. You can see this is now much lower dimensional than this original image. And obviously, at the end of the day, you're using a computer, and it's just going to be a stream of zeros and ones. So at the end of the day, your features are usually just an array of numbers. Then you've got some choices. If your data are unlabeled, then basically your only choice is to do unsupervised learning, right? So if you don't actually know anything about your data, you don't have any outputs that you're trying to predict, then you are in the realm of unsupervised learning. And that's where you can use things like clustering techniques. This is a visualization technique called TSNE. It's actually a visualization of handwritten digits, so numbers 0 to 9. And if you plot some set of features, you can see there's a lot of separation between them. And if you did then learn some labels, so if you, for instance, took some of these and went, okay, what are their labels, and colored them, then you can see that these clusters adhere very nicely to the different classes. Okay? So you can, like I said, you can use unsupervised learning for data exploration. But most of the time, your data are labeled. Most of the time, when we're talking about machine learning, we're usually talking about supervised learning. And there, again, you have two choices. You might be predicting categories. That's what we're mostly going to be talking about today as an example. Is it a spiral galaxy or an elliptical galaxy? Is it a dog or a cat or a pigeon or whatever? If you have these categories, then you're in the realm of classification. You might, this is an example, a very nice example from a Google image, where it's looked inside the image for objects and then classified them. That's a steering wheel, that's a wolf, it's picked out its blue eyes, a Christmas deer toy, right? So this is a classification problem. If you're not doing classification, you're probably predicting a continuous quantity, in which case you're doing regression. Here's an example of regression from photometric redshifts. So where you might know the spectroscopic redshift for some subset of your data, so some galaxies, but for some galaxies you might not have spectroscopy, you only have photometry, and you can still do an okay job at predicting the redshift. So this would be a regression problem. It's a continuous problem. Now the thing is, with machine learning, regression and classification are actually very similar. All the principles you learn in classification, you can pretty much apply to regression. You'll use slightly different packages, but the core algorithms tend to remain the same. Because if you think about it, I could split up this space. Say I knew my data was between 0 and 1. These are the possible redshifts. I could bin this very, very finely and think about it as a classification problem with, I don't know, say 10,000 classes, with the key caveat that the ordering matters. So all I'm saying is that we're going to focus on classification, but everything you learn can easily be extended to regression. Okay, so let's talk about classification. Say you have an algorithm, and it makes a prediction for your classes of your various objects. How do you know if that prediction is actually any good? Okay. This thing here is called the confusion matrix. It's quite well named because it's quite confusing sometimes. What we have here is a simple two-class problem. Now, of course, you can do multiple classes, and you can compare just one class with the rest. So we're not really limiting ourselves by considering a two-class problem. And my classes are yes and no, positive and negative. That's it. So here's what I've predicted. Have I predicted it to be positive or negative? And is it actually positive or negative? So you can see on the diagonal you have your, and actually this one for some reason is inverted from what we normally do. But this one, so you see you'll have your true positives, so where you got class 1 right, your true negatives where you got class 0 right, and then the off-diagonal terms is where you got it wrong. And the importance of each of these will depend on your problem. You may be working on a problem where false positives are disastrous, right? But you may be working on a problem where actually false negatives are even worse. For instance, if you're trying to screen for rare diseases. So how important it is to be pure versus complete depends on your problem. This is in some sense a political choice. Okay, so given this confusion matrix, here's the next question. How would you evaluate how well your algorithm has done? Just quickly, does anyone have any ideas?
You test it on a testing.
Okay, so you keep
Set.
aside some test set, and you make a prediction on that, and then you compare the prediction with your true values. Great. How do you do that comparison? What you have is a bunch of classifications. What you have is, maybe this confusion matrix. But how do you know if it's done well?
Use some kind of curves like ROCs or AUCs, I guess.
I definitely agree, but you're jumping ahead. Okay. Anyone else?
I would use some examples and just try to choose from there, like Galaxy Zoo.
So once you've got this, you've got an example set, you've got a test set, you've made some predictions. You've said cat, cat, dog, cat, duck, pigeon, ostrich, whatever. And you know what they really are. You know that it's cat, cat, elephant, whatever. So you know which ones you've got right and which ones you've got wrong. How do you tell overall how well you've done? How could you compare algorithms? Well, I'll give you... Yeah, you can compute this confusion matrix, but it's a bit hard to interpret, right? You know, yeah, we obviously know we want the numbers on this diagonal to be bigger than the off diagonal, but how bad is it if there's numbers on the off diagonal? So a common choice is precision, right? You might say, of all the ones that I said were positive, how many did I actually get right? Okay, this is a kind of purity thing. What's wrong with this? Why is this not a great metric? No, wait. Give them a chance. Try and think of a scenario where this wouldn't work well. What's missing? What bits am I ignoring from the confusion matrix? There's pieces here that I'm left out. Yeah? Yep. Okay.
For example, if it was a mouse, the algorithm told you it was a rat.
Right, that's good. So by using something like this, you don't really take into account the ones that you only get a little bit wrong. Okay, good. What else? How could I cheat? I can cheat with this one. Okay, go for it, Ewan. It's okay.
I was just going to say that the weightings. Oh, sorry. I was just going to say you might want to consider some kind of weightings in the case that it cost you more to make a false positive than if to call it a true positive.
Yeah.
Like an example I was just reading about in the BBC News was that there was a lot of false positives for lung cancer in a UK hospital, and obviously the cost of that is perhaps much greater than a you know.
That's very good. That's very true. Your metrics should really depend on your problem, and your cost for false positives versus false negatives may be very, very different. And how you make that choice is somewhat subjective. It's a little bit kind of like it's a subjective choice. But what I'm actually going for here is that you can game this by just being very, very strict. By just saying, I need to be really, really, really sure before I'll consider something to be a positive. And then you could get beautiful precision. You could be 100% pure, but you've picked 5 objects out of 1 million. So that's obviously not a good metric. So there's another metric people use a lot, and that's accuracy. This is better because we're taking into account the whole confusion matrix. We're saying of all of the classes, how well did we do? What's wrong with this? How can you game this? Make accuracy really, really high and not make a very useful algorithm. Guesses are fine. If you sort of have a vague idea, give it a shot. Sorry? Very good. If my positive class, say that's the one that I really care about, is unbalanced, so it's a very small percentage of all of the objects that I'm looking at, you can arbitrarily make accuracy really, really high. So, an example of this, again, to go back to diseases, if you had a very rare disease, and you say, I want to have very high accuracy of detecting whatever, HIV, say. But the prevalence of HIV is a tiny percentage. So I can just arbitrarily say, okay, nobody's got HIV, and I'll get 99.999% accuracy. And that's obviously not what we want, right? So an example like that is obviously where Bayesian statistics is much better because you can incorporate the prior. But you can use better metrics that are less sensitive to unbalanced classes and are less sensitive to you being able to give an arbitrary purity cutoff. And so it was mentioned at the back, my personal favorite, and what's commonly used in the machine learning literature, is ROC curves. So these are receiver-operator characteristic curves. As far as I can tell, the name has nothing to do with what the curve is. It's like a World War II term, apparently. So instead of making a number, you're now making a curve, and that's much better. And I'll explain why in a minute. What are you looking at? On the y-axis, you're looking at the true positive rate. This is completeness. And on the x-axis is the false positive rate. This is not actually contamination. So I should put sort of contamination here. But if you have a high false positive rate, then we know you're doing quite badly. How do you get these lines? In my example where I said cat, cat, dog, pigeon, ostrich, whatever, whatever, what my algorithm would actually give me is not this is a cat. It would give me a score or a probability to say, I'm sort of 80% sure this is a cat, or I'm only 40% sure this is a cat. And now what most algorithms will do by default is give you a cutoff at 50% and say, okay, if it's greater than 50%, it's this class, otherwise it's this class. Or, depending on, it'll just take the highest probability. But you don't have to do that. You can choose where that threshold should be. And changing that threshold is what gives you these curves. So I'm a cosmologist, and we do type 1a supernova cosmology, which I'll talk about later. And for us, a 50% probability that this is a type 1a is nowhere near good enough. If you want to have a really pure sample, it's really important. So we'd want to have like a 95% probability that this is a 1a. That would put us over here. We'd be very, very strict. So we'd be very pure, very low contamination, but not very much completeness. But you might say, oh, maybe I'm looking for funny objects, so I want to be as complete as possible. Just filter out the worst rubbish, and I'll look at the rest. If you want really high completeness, you're going to be over here. You're going to have a much lower threshold, like 80% or something like that. And you can see that this faint curve is kind of rubbish, and this dark curve is really good. Why? Because I can be very, very pure here and be very complete. Whereas here, to get that same level of completeness, I'm very contaminated. This, if you ever see a ROC curve with a line like this, it's not doing any better than random. If the line goes the other way, it's doing worse than random. And you are really doing something wrong. So what you want is a curve that's as close to this left-hand corner as possible. And if you integrate under this curve, you get this thing called the area under curve, which is a nice way to summarize it in one number. And if I remember correctly, the technical interpretation of AUC is if you took an object that you knew was positive, the AUC is the probability that your algorithm would assign it as positive. So if your AUC is 95, you've got a 95% chance of getting it right, which is pretty good. So that's how you can interpret these numbers. If it's anything above 0.9 or so, you're looking in the pretty good regime. Depending on the problem. Some problems are really difficult, and so historically they don't have very high AUCs. Does anyone have any questions about this? If you don't have any questions, ask yourself, why don't I have any questions? Is it because I understand everything?
My question is, why is this presented as being something special when it's like so incredibly basic?
I agree, it's extremely basic, but you would be surprised at how often accuracy is used as the metric, right? It's especially in deep learning papers. So these are common in machine learning, and it's very obvious, but they're not always used, right? Accuracy is just easier a lot of the time. Yeah, Corin.
So I agree with the use of this statistic or measure. But of course, it's still just one number that's trying to capture four different things.
If you just look at the AUC, yes.
Right. So well, we can talk about this offline, but I mean, are there cases in which you are actually using multiple objective measures in your machine learning?
Yeah, I mean, absolutely. You could design, and in fact, in scikit-learn, there's functionality to design your own metric, whatever you want to optimize for. Your problem may, for instance, be, I only care about this regime of the ROC curve. So the thing is, what I've plotted here is ROC curves that don't overlap, but in general, they do, they can. There will be a region of the ROC curve where one algorithm does better than the other, and a region where they swap. And if you care about this region, then you don't care that maybe overall the AUC is the same or the AUC of the other one is slightly better. But in the region that I care about for my problem, I want the best algorithm. So definitely, and I think there's not enough focus of this, of designing your metric for your problem.
So I think this is a case for, for these algorithms giving probabilities because, different users will have different requirements in terms of contamination completeness, etc.
Absolutely.
But of course, for training the algorithm, you need, for most methods, one scalar metric to optimize, right?
Yes, yeah. Yeah, you do have to make a choice. These are optimization algorithms. There's no concept of marginalization here as of yet. But you do have to make that choice for what metric to optimize. But at the end of the day, you can produce these probabilities, and the great thing is that you can start folding them into your analysis further down the line if they're calibrated. Yes, question?
I can't just think about a problem where I'm not interested in having the lowest false positive rate.
Oh, yeah, you could definitely think of a problem with that. So say for instance, I'm applying this to artifact removal in images, right? I want to get rid of junk. Airplanes flying over, CCDs acting weird, cosmic rays, whatever. I definitely don't want to be too strict there, right? I want to be as complete as possible. I just want to throw away the worst junk and then get a human being to maybe look at the rest of it, because you don't want to be throwing away too much of your data, right? So it very much depends on your end user case, right? In the case of supernovae, what you'll see is we'll produce these ROC curves. For cosmology, I want to be here, but I don't know, maybe you're interested in the astrophysics of supernovae and how they relate to their environment, and you want as big a sample as possible because you want to do statistics later on, right? Then you might put that cut quite low, so you get as big sample. You know there's going to be some contamination, but it's okay because you're actually doing investigative studies rather than sending this down the line in cosmology. Question?
This is for a classification problem, right?
Yes.
But does it hold also for a clustering problem or?
For what kind of problem?
Clustering.
Well, for clustering, there isn't really metrics as such that I know of anyway, because you're unlabeled. You don't know what's true. You don't know what's right. So you can't really say my algorithm is doing better or worse than another. I mean, you could compare them. You could look at them and be like, oh, this algorithm's made these rubbish clusters that don't visually separate, but this one's done a good job. So you can do things like that. But you, in general, wouldn't use something like a ROC curve. You also wouldn't use this for regression, because regression, you're predicting a continuous quantity. That's easier. You could do something like a mean squared error.
You can take this clustering algorithm with a simulation, so you know what you have to get in principle. You could apply.
You mean like actual physical clustering in the universe, or what?
Yes.
Yeah, sure. I mean, you could do something like that. I mean, you could create a classification problem out of that, but that's not what we would call unsupervised learning then. Did you have a question? Yeah.
This is probably a really stupid question, but
That's perfectly fine.
I completely do not understand how these curves are derived.
How are they derived?
Yeah.
Great. Okay, so I didn't actually put it on here, I'm sorry. The true positive rate and the false positive rate are both derived out of the confusion matrix, right? So, and I have to be completely honest here. I find the confusion matrix confusing. I use Wikipedia as much as, for distributions. I use it for confusion matrix to remind myself what is the precise definition. So I just suggest look it up on
Yeah,
Wikia.
I understand that. So for a given algorithm, for a given data set, I can compute, a given false
I see. So how do you get the different points on the curve?
Yeah, how do you get the different curves?
Okay, brilliant. I understand. Sorry. So what you would do is For each object in your, say, test set, we'll talk about training test sets in a minute, but for each object, your algorithm will give it a probability or a score, right? Then what you do is you basically change your threshold for what you decide goes into your positive or negative class. So your threshold at this point in the ROC curve is very high, so it's backwards. So your threshold here will be like 0.99. Your threshold here will be 0. So your threshold here says, I classify everything as positive. So for each threshold, you'll see that you generate a new confusion matrix, because now effectively you have new classifications. So I say, okay, this has an 80% chance of being a cat. When that threshold is 0.8 and above, or when it's 0.8, then it's going to be classified as a cat. Anything lower, it's not. Right? So your confusion matrix changes for every point on this ROC curve. And so you can calculate the true positive and false positive rates.
Thank you.
Can I add a comment before I give you the mic? If you think about, you can think about it having two curves, two distributions that overlap, and moving the line between them from one side to the other.
Yes, exactly.
So you're like, you have two distributions that overlap, and you're moving the line this way. So you're having more of this and less of that, and this is how you determine your threshold and how much of each you're going to have.
Hi, I have a thought that was about the beginning of your talk, so not about ROC curves and things. You said that machine learning was good or useful because a lot of the time the data and situations are so complex that it's very hard to like design your good statistical model to do things in that way. The way I think about the machine learning tools is that they are models. They're just ones that happen to be very flexible so that they basically work on most things.
That's true.
Do you agree with that?
I would actually go one step further and to say they are prescriptions for building models, right? Because, you know, when I think about a model, I think about, okay, it's, you know, it's an equation or a bunch of equations with some parameters. But the actual equation can change during training. For something, for instance, like a random forest, where your decision trees, which we'll go into, which might be different depths, et cetera, et cetera. So your equation actually changes. But the prescription for how to build that model is what the algorithm is. Yeah. Okay.
So what does it mean when two of these curves are overlapping? Some kind of curve just moves down and then like that, and then some other curves are more like that. Maybe I draw it on the board?
Yeah, sure, go ahead. Great. Does anyone have any other questions while Antle's coming up? Yes.
So how does the probability actually factor in? So in this case, for saying that a true positive would be, I don't know, if you like have a signal to noise of 5 sigma, that would be like if you say it's Gaussian, that's a so-and-so % probability that it's a real thing, then it would be above a certain threshold. Is that how?
So you're saying, how do you interpret those probabilities?
In terms of what the noise or the uncertainties are.
Yeah, that's a very good question, because the reality is that the probabilities that come out of machine learning algorithms are in general not calibrated. So they don't necessarily mean anything. So, well, not they don't mean anything, but if I say there's an 80% chance that this is a cat, it doesn't mean in 80% of all universes or in some kind of frequentist interpretation, 80% of the time I will be right that it is actually a cat. So this is actually like a whole different kettle of fish and a whole different field for how to calibrate these probabilities. And I would say it is dangerous to assume that they can be interpreted in the same way as, you know, we would talk about Gaussian probabilities. That being said, there is research on this and there are ways of calibrating them so that you can use them further down the line. But I would say that this is where we as scientists really need to be scientific in interrogating these probabilities and making sure they're meaningful. Okay, so Antla, what was your question?
When I'm just talking about how good is my classification, if these outbursts I'm measuring is a supernova or kind of some other stuff, how do you would like to analyze this when these curves are like that, like because the AOC is something like the same, and it's kind of different at these different sections.
Yeah, exactly. So this precise one, I don't think can happen mathematically, but if I just change it slightly, and you say have this curve carrying on here, so they cross once. All right, so say these are the same. This is exactly why ROC curves are useful, because if you just use the AUC, they have the same AUC, so I'll pick either algorithm, who cares? And this is where, again, what we were talking about, what you actually want in your problem, it defines where you would look in the ROC curve. So maybe, like for supernova cosmology, I care about purity, so I'm only going to look here. And maybe then I actually want to be using a different metric. I want to design a different metric that's got something more to do with the purity than, like the ROC curves and AUCs are great for overall in all kind of situations which algorithm does better. But if you know the situation you care about, you can design a metric to only look where you're interested. So it's actually very useful to understand, for ROC curves to help you understand where different algorithms are doing well and where they're doing badly. Go on.
So we just had a little conversation here. So I think the only constraint on the ROC curve is that it has to go from 0 to 1, and it has to increase monotonically, or rather not decrease. But I think they can cross arbitrary times. Or can you convince me otherwise in 30 seconds?
I probably can't convince you otherwise, but
Okay.
I've never seen it.
Okay. We'll think
And I'd
about
have
it
to, I'll think a little bit about it. Yeah.
It's not such an important point, but
Yeah, I've never seen it. I've definitely seen them cross
sure,
once, but I've never seen this behavior, because it would involve it. Maybe with a very pathological data set, it would involve it doing extremely well suddenly at this end of,
and maybe
of the threshold.
some pathologically weird algorithm that did stupid things.
Yeah, I have to say I've never seen that, but it certainly may be possible. Okay, any more questions before I carry on? This is great. Keep asking questions. Everyone said they enjoy discussions, so. Okay, so we're going to go through a couple of algorithms. I have purposefully chosen not to go very deep here. So I'm not going to go into very technical detail as to how these algorithms work. I'm going to give you an idea of how they work. I really recommend that after these lectures you go back and study them and don't just use them as black boxes. Really understand the choices that are being made and the choices in the implementation that you're using. But my goal is by the end of today, I want every single person in this room to be able to run a machine learning problem end to end so they could apply it in their research. So we're not going to go very deep, but I'm going to give you an idea of how algorithms work. There are hundreds of machine learning algorithms. These are 3 that I've picked because they're all very different from each other. So it shows you how very different things can all work as machine learning algorithms. So we're going to start with k-nearest neighbors because I personally feel like this is basically the easiest algorithm you can think about. And again, just take note of this is where to look in scikit-learn if you want to use it. So say you've got 2 classes, stars and squares. This is my training data. So this is data that I know the labels of. I know what's a star and I know what's a square. And imagine this is some 2-dimensional feature space. Now I give you a new point in feature space, and I say, what is it? Is it a star, or is it a square? K-nearest neighbors is very simple. All it does is it looks at the k nearest neighbors, in this case k is 5, and it counts. And it says, are there more squares, or are there more stars? If there's more squares, we'll call it a square. It's as simple as that. And you can see how this can work because, just because if it's embedded quite deeply into this cluster of this class, it'll very obviously come out as a square. You can be a little bit more sophisticated by weighting your neighbors by inverse distance, and you can use different distance metrics. So there are more sophisticated versions of this algorithm, but at its core, this is all it's doing. And you can get a probability of belonging to a particular class by a kind of normalized number of votes for that class. Okay? So you can imagine the more squares that surround it, the more I believe that it's likely to be a square. The great thing about k-nearest neighbors is conceptually very simple. I just explained it to you in 20 seconds, and I'm pretty sure everyone probably got it. It's very easy to tune. You know, there's not so many of these hyperparameters. It suffers very, very much from the curse of dimensionality. Can anyone see why? Why would it struggle in high dimensions? Sorry. Yeah. Antler?
Next neighbors in more dimensions than kind of 3 dimensions. It's hard to recognize for yourself what's kind of next neighboring, and you need to formulate them before.
It's not quite. You would use the same metric in high dimensions as low dimensions to define nearest neighbor.
It depends on your projection. Like, for example, if you're looking from one view, from one point in space in higher dimensions, I'm here.
Yeah. Sorry,
you might find that your point is more affected by the neighbors if you're looking from one point of view than if you're looking from another point of view. Like the weights would change.
Sort of. It's not obvious how. Can you all hear me? Okay. It's not obvious how that would. Yeah, I'm not too sure that's obvious that that's what happens in the high dimensions. More neighbors, well, less neighbors, right? Well, you have the same number of neighbors, but everything, so as Brendan said, everything's just far, let me put it this way. Computing distances is hard, right? As you go into higher and higher dimensions, everything effectively becomes arbitrarily far away. So anytime you've got a distance metric in your algorithm, it's probably going to suffer at high dimensions. And in general, k-nearest neighbors is simple, but it's actually not really that good. It's okay, but it's not really that good. Question at the back? Oh, do you want to wait for the microphone?
Sorry, if you're trying to generatively assign classes to your different unknowns, it wouldn't work if you have. So it would depend very much on where you start assigning your classes, right? Because if you have, for example, your initial true values are just 2, for example, and you have 100 which are unknown, it depends on what you start assigning these values to where they will be. So let me explain this. Imagine that you have a point far to the right and another one point far to the left. They belong to different classes, and you have a bunch of points in the middle. And then it depends on where you start assigning your classes.
So you're saying it depends on where you decide the decision boundary to be? Is that what you're saying?
Yes, sort of. So if you start with just 2, right, and then you have a lot in the middle, right, then you start from the right, then it will say, okay, so probably I'm
no. I think you may be misunderstanding. So this, potentially, let me maybe explain again. The stars and the squares, I know what the classes are. That's my training data. This point here, I know where it lives in this feature space. I know what the feature values are. So it's completely well defined as to which are its nearest neighbors. You just compute the distances, right? The thing that's hard is that you've got to compute the distances to everything before you can figure out what's the nearest neighbors. So there's no choice about where to start here. So I don't think there's any elements of that. So you're saying if you update your training set, yeah, that's true. I mean, that's kind of online learning, and that's not generally how this algorithm, it can be used that way, but yeah. So k-nearest neighbors is okay, but for high dimensional space, it's not something I would use. The next algorithm I want to talk about is decision trees. I really like decision trees because I actually think this is how, as human beings, we like to classify things. You know, if you think about it, if I say, here's an animal, classify this animal. Well, I mean, if we know what it is, it might just be like it's an elephant. But if you think about it in biology, you know, if you go back, for me, back to high school, how did we classify things in biology? You know, we had you basically ask questions about it. Is it warm-blooded, cold-blooded? Does it lay eggs? Does it give live birth? How many legs does it have? Is it furry? Does it have scales? Does it fly? Is it microscopic? We kind of ask questions, and as you go down with each question, your answer is yes or no, or it might be quantitative, it's got 6 legs or 100 legs. And as you answer each of those questions, you split your data more and more finely, right? If I started with all the animals in the zoo, and I wanted to classify them according to this structure, you would start asking those kind of questions, and you would split it up until eventually you get to your one animal and say, okay, that's an elephant, because it's got 4 legs, and it's warm-blooded, and it is whatever, et cetera, et cetera, et cetera. So I think decision trees are quite an intuitive machine learning algorithm, because this is how we as humans tend to classify things. So here's some arbitrary feature space, whatever HT is. And the first node says, is it, I don't know why it's only less than 242. I don't know what happens if it's greater than 242. Apparently we just throw it away. But anyway, so then you decide, does it pass or fail? And if it passes, we might ask a different question of it, because this question might not be relevant if it passed. If it failed, we'll ask this question. Until eventually you end up with what's called a leaf node, where you decide, okay, this belongs to this class. Now the one question is, how do you actually do this automatically? Because it's actually a little bit not obvious. Like the algorithm seems quite obvious at first, but then when you ask, how do I do it automatically, it's actually a little bit tricky. You have to decide, if you have 50 features, at each point you have to decide which feature am I going to use to make a decision on. And then once you've picked that feature, you've got to decide, okay, what decision do I make? If it's categorical, how do I decide which category puts it in which direction? If it's a quantitative thing, I've got to decide, do I split on 0.2 or 0.3 or 0.5? How do you make that decision? So there's some well-defined methods using this thing called the Gini impurity or the entropy, which basically defines a kind of splittiness of data. You want to make a decision that splits your data really well. If you make a decision that puts 100 objects in one bin and 1 object in another bin, that's not so great high up the tree. You'd rather make a decision that puts about 50 in this one and 50 in this one, and then I can keep going down. So you want to be able to separate out the data as well as possible between your different classes. This is a little bit technical, so there's some extra slides at the end you can go look at, and I recommend just reading up on this a bit. Once you have the tree, making a prediction is quite simple. You just start at the beginning and you ask all those questions. Is this feature less than 0.2 or greater than 0.2? Is there 4 legs or 6 legs? And so you just propagate your way down the tree until you get to figure out which node am I at, and that's my class. Decision trees are great. They're conceptually relatively simple. They do tend to produce really overcomplicated trees. They are very prone to this thing called overfitting, which we're going to talk a little bit about later. So these are actually not a very good machine learning algorithm, because they tend to be very biased, right? So you might train it, and it does really, really, really well on your training set, but then you try and apply it in the real world, and it'll do horribly badly, because it's so overcomplicated. Yeah?
Can you have the same leaf at different points in the tree?
The same leaf at different points? You mean the same class?
So I mean, I thought a leaf is a final state, and can you reach the same leaf later on up the tree? So it could be attached at 2 different places, the same leaf.
Can be attached at 2 different places. Oh.
They're equivalent, basically. If you couldn't decide at a certain stage, but then further up.
That's a good question. I don't think so. Yeah, no, I don't think so.
You call them different leaves, even though.
Yeah, you might end up in the same. You might end up in the same class, but effectively, when you propagate down, it's deterministic, should I say? So your question is, can you take multiple paths down to the same leaf? you come back to this exact leaf. No, I don't think that's within the structure. Yeah. Yeah.
Forbidden to repeat the question.
It's forbidden to repeat the question. Yeah. I like it. That's well phrased.
Maybe I don't understand the question, but you don't need to come back to the same leaf, right? Because
Yeah.
all you're interested in is classification, so you can reach the same class by many different routes.
Yes, exactly.
Right, so this is a two-class problem, right? I think the
Yeah.
leaf and the round, blue round thing, isn't that right?
Yeah. So,
With probabilities, sure, but you don't, there's no, you could have in practice there may be a much more complex tree. You may have another leaf somewhere which also ends in P
Yes,
equals
yes,
0.82,
yes.
but by a different route.
Sorry, yeah. Yeah.
Were
Yeah.
unique,
So,
no.
so if you answer no to this, it does not preclude you from becoming a leaf class, right? Later down the line, right?
You can still become a
Yeah.
leaf.
You can still be a leaf.
You can be a
dream.
leaf.
Yeah. Exactly. So you can go, and this often happens. If it's just a more complicated part of the data, it will go further down the tree. Yeah. Sorry, thanks, Corey. Okay, so how do you get around with these things not actually being that good? Well, you use this amazing thing called ensemble methods that are proven to be extremely effective in machine learning. So one tree is bad because it's biased. 200 trees is pretty good. So what you do is you run multiple decision tree algorithms. And there's an element of randomization here. And that element of randomization, as far as I can tell, depends very much on what implementation you're using. So check carefully. But in general, you would randomize which subset of data the tree gets. So not every tree sees all the data, all the training data. You might even randomize which features it's allowed to use so that it doesn't become kind of overly dependent on any given feature. So you get hundreds of trees, all of them a bit different. And all of them will give slightly different predictions. And then you say, okay, how do we combine them? And there are lots of different ways of combining decision trees. So here's an example of a few different decision trees. And here is what we would call decision boundaries. And these are great ways to visualize machine learning algorithms. Say we've got these this feature space of two features. And you say this tree says, if you're in this region of feature space, you're in class 2. This tree says, if you're in that region of feature space, you're in class 3. This one's got kind of a weird decision boundary. And then you need some way of combining all of these together to get the final decision boundary. You should be able to intuitively see that if I have one crazy tree that says, this is C2, but 90% of the other trees all say, actually, it's C3, that should win out. That should be the more likely classification. So this helps you generalize your decision trees. How you do this averaging depends on the algorithm that you use. There's one called bagging, which is quite common. Random forests has a sort of version of bagging. There's one called boosting, which actually, the way it does the averaging is actually the way the whole algorithm runs is it focuses on data that's difficult to classify. So data that's maybe not so well separated. Anyway, so you can read up on different methods of averaging and ensemble methods. Random forests is a very, very good classifier, and it's very commonly used. And this is a way of building lots of decision trees, subdividing out the data, et cetera, and averaging them together to give you a very robust classification. So in general, ensemble methods, and particularly, so you can use ensemble methods with different, they're called learners, different machine learning algorithms, but they're very commonly used with decision trees and they're very effective. These are very, very robust algorithms. They're able to handle, theoretically, mixed feature types. So you can imagine it doesn't make a difference whether I make a decision on a quantity or on a category. But I will say that in scikit-learn, the implementation actually doesn't let you, unfortunately, use mixed features types. It's robust to high dimensionality. I've thrown quite high a large number of features at random forest and does quite well. The nice thing is you get out this concept of feature importance, which helps you interpret your algorithm. It will actually tell you how often it used a feature to make a split, right? To make a decision. So how often that feature turns up. And you can imagine that if it turns up a lot, or if it's really good at splitting data, it's an important feature. So you can actually learn about what is it that is driving your classification. And I'd say one of the best advantages is random forest is my favorite algorithm. So I would usually say it's a good algorithm to start with if you're starting a machine learning problem. Disadvantage is it's a bit computationally expensive. Now, when I'm talking about computationally expensive, I'm talking about it might take a few minutes. So it's not really intense, but it does take a bit longer than some of the other algorithms. It does have, well, I wouldn't say lots. There are a few hyperparameters. There's things like how many decision trees do I put in? How deep do I allow the decision trees to go? How many features do I allow to choose from at each leaf node? There's a few parameters in there that do have an impact that you need to play around with. That's a very, very good question. How much data is enough data in general for machine learning? It depends on your problem. It actually doesn't so much depend on the algorithm unless you're using deep learning. It depends more on your problem. So if you have a very kind of easy problem where the classes are separated very easily and there's not much variation in the class, you don't need a lot of data, right? So the supernova example that we'll do later, and that I've published on, there was 20,000 objects in my test set, and I only used 1,000 in my training set, and it was beautiful. It was very, very good classification. But it really depends on your problem. If you've got a lot of variation in your classes, you need a lot of data to capture that variation, right? And so how much is enough? It's hard to say. You know, quite a lot of the time, we're limited by what's even possible. Like how much training data can we even possibly get? And you can kind of test your sensitivity to your amount of training data by withholding more and more of it from the algorithm and see how well it does. I mean, I would always recommend, we'll talk about things like cross-validation, etc. I'd always recommend using different bits of your training data, holding out bits, and seeing how sensitive it is to it. And that will tell you kind of, in general, do you have actually enough? Good question. Okay, any more questions on random forest? We're going to move on to neural networks. Yeah. Oh, you want the... Told you I was going to make you work hard today.
But the graphic you showed before, it seems that...
This one or
yeah,
one?
this one.
Yeah?
This one. It gives you the sense that the data has to be linearly separable.
That's a good point. So in your feature space, you know, say you had a two-dimensional feature space and you plotted your data and colored the points by your different classes. If they're all on top of each other, pretty much no algorithm is going to do a good job, right? If you only have these two features and you plot them and they're on top of each other and they can't be separated out, statistics isn't going to do a good job either. And machine learning is not going to do a good job. There does have to be some separation. The problem is it's quite hard to actually tell beforehand if there is good separation between your classes. And I should also say they don't have to be linearly separable. That's definitely not true. Is that your main point? Yeah. They definitely don't have to be linearly separable. I mean, look at this. I've got class 2 here, I've got class 2 here. You know, you can get really weird decision boundaries.
But this is because of the number of trees you have, so how much trees you have, you're going to have...
No, it will depend on your... I mean, to a limit. If you have very few trees, you may not have a very good decision boundary, but it will depend on your data. It will depend on where your data is clustering, and it can be very complicated. And also remember, this can be very high dimensional. This could be 50 dimensions easily. And it very much can be nonlinear, and this will still work. That's sort of the point. You wouldn't really need a machine learning algorithm if your features were beautifully linearly separated. And you just draw a line. You say, if it's less than this, it's this class. If it's greater than this, it's this class. Done. I mean, that is machine learning. It's just very easy machine learning. So in general, this decision boundary is nonlinear. And you can learn it with any of these algorithms. They'll all do nonlinear decision boundaries. Anything else? Okay, let's do neural networks. I know lots of people are like, yeah, neural networks. It's funny because these things, I mean, this is the oldest machine learning algorithm, I would say. I mean, I could be argued with. Neural networks is really the oldest thing that we would say is a machine learning algorithm. And for years, they're popular, and then they were like, nah, these are useless. And now they've come back. They're the really exciting algorithm. So this is the simplest neural network, version of a neural network, I should say. These are, in theory, based on how we think the human brain works. In practice, I don't think we know how the human brain works, but supposedly that's the inspiration behind it. You start with your input layer, which has some features. These are your x values. You have your output layer, which is something. This could either be a classification, a label, or it could be regression. In the middle here, I have a hidden layer of neurons, right? Each neuron connects to every single input, and each neuron is in turn connected to the output. What makes up a neuron? Well, it takes each input, multiplies it by a weight, all right? And learning the weights is what happens in training. You don't generally know what they are a priori. So you have a weight, you multiply it by each input, add them up, put it through an activation function. So this is the kind of biology bit. You know, we have this concept that neurons switch on. They switch on and off. So this activation function is a thing that goes from 0 to 1. How switched on is this neuron given this weighted sum of inputs? So typically, we would use some kind of sigmoid function. So tan h is very common, but there's no real reason. I mean, okay, there are reasons, but you can use different functions for activation functions. So you've put in this weighted sum of inputs, activated it, and that produces some kind of output, right? And that's all it is. So each neuron is actually just applying this kind of transform to the various inputs. And to train it, you need to learn these different weights. You can see there's quite a few of them. So these are great because they're also fairly robust to high dimensionality. What's interesting is there's actually a Bayesian interpretation of neural networks, because it really is just an equation that you can write down that has some parameters. So you can marginalize over these parameters in exactly the same way you've been learning. And McKay actually did this, I believe, a part of his thesis on this. So they're very nonlinear. They can learn very nonlinear decision boundaries. So these are very good algorithms. They work well for a lot of problems. Again, it's computationally relatively expensive. If you have very complex networks, like we're going to talk about later, you need lots of training data. You need, I would say, probably at least an order of magnitude more than you would typically for a normal machine learning algorithm. And they can be a bit difficult to interpret. I mean, you can write down this equation, and you will, in one slide, write down this equation, but it's a bit difficult to know exactly what it's doing. You know, what are the features that are important? How is it making its decisions? They're a little bit black boxy. Okay, I've talked too much. Now it's your turn to do some work. So here's a question. You can just do it on pen and paper. Here is a simple neural network with inputs, a hidden layer, and an output. I want you to predict the value of this output given these inputs and given a tan h activation function. So you have my notes. They're in the GitHub repository. So you can look at the previous slide. And you should be able to write down this output in terms of all of these. Have fun. I'll give you, I don't know, 10 minutes maybe. Okay. All right, is everyone done? Nod if you have an answer. Just nod your head if you think you got it. I know of at least like 5 or 6 of you who have got it because I've seen it, and you're not nodding. So just nod your head, you got it. Yes? Got a few nods? Does anyone feel brave enough to come and write it on the board? Suddenly he's shrinking down. No? No takers? Okay. That's fine. I understand. I probably also wouldn't want to come write it on the board. But check yourself, and if you didn't, I'm going to go through the answer now. If you didn't get it right, talk to your friends afterwards at tea or come talk to me and try and understand why you didn't get it right. Don't just give up on it. Let's start with H1. What does the output of H1 look like? Well, remember I said you take the weighted sum of the inputs, that's W1 times I1, W2 times I2, add them together, apply a tan H. So that's the output here. Now let's look at H2. Same thing. W3 times I1, W4 times I2. Apply the tan H. So now the last step is how to figure out how to get the output from O1. It's just the weighted sum of its inputs. Same thing. So we add these two pieces together, multiply by the weights, and add a tan H. And that is the output for O1. And so if you think about how this works, first of all, you notice that this output is between 0 and 1. So you can imagine if you had a 2-class problem, if this number is quite close to 1, then you say, okay, it's the positive class. If it's quite close to 0, okay, it's the negative class. You can see that what happens is you choose your weights such that this function changes depending on what your inputs are. So if your inputs belong to a particular class, neurons will light up differently. I say light up, they will activate differently. In this very simple case, probably for class 0, they will both be quite low. But you'll have very much more complicated networks, so it's a bit more complicated to interpret. But so different neurons light up for different classes. When I say light up, I mean their output is high. And this is kind of how the human brain works. You know, you can do MRIs, and if you see a picture of a cat, your brain will light up differently compared to if you see a picture of the dog. Sort of. So this is how a neural network works, and it's a really nice example because you can write down in one equation the actual function of the machine learning algorithm. Yeah?
A quick question. Where does the last tan H come from?
So this is also a neuron. This output is actually also a neuron. So if I don't have the tan H, this number can be sort of anything, you know, depending on these weights. The tan H is the activation function which tells me how switched on this neuron is, which gives you your final probability of belonging to that class. And this final activation function will be different depending on what kind of problem you have. A regression problem will have a slightly different function. Yeah?
Yes, answer a quick question. Is it needed that all the neurons, or all the layers has the same activation function?
No. In a simple multi-layer perception, yes, that's true. We'll do convolutional neural networks very briefly this afternoon, and that's not true. You can have different activation functions. Yes. Do we have a microphone?
So it's the tan H function that gives you the output of the neuron, but the neuron is not either switched on or off. So there's no if, like in each neuron, there's no if it's switched on, it outputs something. If it's switched off, it doesn't output.
Yeah, no, it's just a continuous number. There is a kind of activation function that you can use, which is like that. It's either 0 or 1. depending on these inputs, but that's not this activation function. This function is a smooth function between 0 and 1, so it will be a continuous quantity. Yeah.
Are there uses where people use different activation functions for different layers? So say I liked what tanh does, but then I knew that my output wasn't classes, so I might want to map it to the whole real line or something.
Yeah, so in a regression problem, obviously, you wouldn't use a tanh because you're actually trying to get a number out. So there's a slightly different activation function you'd use here. And again, in convolutional neural networks, you might use different kinds of activation functions at different points in the network. Actually, there's quite a lot of things that you can do there. There was a question, I think, at the back. Yeah? So how do you choose an activation function? Yeah, that is actually a bit technical. Yeah, so I've just repeated it, so it's fine. It is actually a little bit technical, and I read up on this once, and you get into a lot of actually computing performance. You get into the land of computing performance. That actually drives the choice of the activation function. You know, in simplest terms for a problem like this, where we think about how switched on is a neuron, you just want a smooth function between 0 and 1. You know, you want it to be, that's it. That's all the requirements, which is why sigmoids are quite popular. But the actual choice of exactly which function to use depends on the implementation and depends on computational performance. And there's a lot of articles on it. If you want to read about it, there's like a huge amount of machine learning literature has gone into choosing activation functions that are fast, basically.
So the ROC curves you get in the end, they do not depend on the activation function, it's just a performance issue, or?
Yeah, so at the end of the day, ROC curves are completely agnostic to what goes into your machine learning algorithm.
And the activation function?
No. Because at the end of the day, you end up with, so what you'll do is you'll take a number of different test objects, right, that all have different features, push them through this network, get out an output, which is a number between 0 and 1. That's it. Your actual details of what you've done in this network will change the performance, but doesn't go into computing the metric. All that matters is how do I classify it? Question at the back?
Just to get to reiterate, to understand well what you were saying is that this this gives you basically not the answer or not the result, but the firing of the neurons, right? Like a certain path towards your result. Like it gives you that these set of neurons are firing more than these sets of neurons, and so there's more probability for the result to be this, given those neurons.
Yeah. So at the end of the day, you get out a number here, but it's not cat or dog. It's probability of being cat or dog. Yeah, exactly. Any more questions? Yes. Do you want to maybe wait for the microphone? I can hear you a bit better.
Thank you. Hi, thanks. So just, would O1 there just be probability of cat? So if you got 0.7 there, you just have probability of cat, and you need another O to get the probability of dog?
Yeah, multi-class classification is, it's not hard, but there is a slight complication there. Yeah, you do have slightly different outputs here if you have multiple classes.
Okay.
More than 2 classes. Yeah.
Thanks.
There's a question here. Sorry.
A simple question. Is it possible to get uncertainty estimates on your probability at the end?
Great question. So the machine learning literature has been quite fun to follow in the recent years, because for a while everyone's like, convolutional neural networks, deep learning, it's amazing, look at the accuracy, look at the accuracy, look at the accuracy. And now people are like, how do we really interpret these things, and how do we use them, and how do we test robustness? And so this question of how much do I believe this probability is really important. In neural networks, you can, like I said, you get these things called Bayesian neural networks, where you can marginalize over these weights as parameters, and you can get out, you treat your probability as another variable, another parameter that you can get a distribution over, right? Those are very hard. They're very computationally intensive. You can imagine these networks can be deep. There can be hundreds of parameters. In the case of CNNs, there can be a billion parameters. So trying to do that kind of properly is quite hard. But there are other techniques that people are using to kind of get better interpretations of these probabilities and kind of uncertainty estimates on them. You really want your algorithm to be able to say to you, look, I really don't know. You know, like I've got this probability, but I just don't know if it's right. And so there is actually a lot of work in the literature towards this. But I would say it's not standard at all. Normally people just get out a number and just go with it. Yes. Microphone? There.
So 2 questions related to that. When you say that the output of O1 is the probability, is that the posterior probability given what, and or is it another probability? And why? So it's a bit hard for me to understand why you would need the uncertainty on that probability if, like, the algorithm would just give you 0.5 if it doesn't know, or not.
Yeah, not necessarily, right? These algorithms can be biased in weird ways, right? So it might give you 0.8, but it actually not be a very good estimate. And in terms of what this probability actually is, you know, that's also up to debate. Like I said, calibrating these things and interpreting them is quite hard and is still an active field of study. You know, so it could be considered the probability of this object being of this class given the training data, the architecture of the network, the choice of the activation function, et cetera, right? So you could consider it the probability given all of those things, given all of those assumptions. Yeah, Brendan, you want to add something?
Yeah, I'm not sure if this is 100% correct, but it's my impression, and it gives a way of thinking about neural networks for people who are more used to statistics. So if you think about it as something a bit like a logistic regression, where you had that the probability of being in a certain class is some function of the inputs, then I think that probability you get for a fixed value of the weights would just be the conditional probability that you would use to predict new data given those values of the weights. And
yeah,
then
and given the training data that you've used.
And yeah, but it's something like based on a point estimate of all the parameters.
Yes, it is exactly based on a point estimate, yeah.
Yeah, and then the uncertainty you were talking about would be, well, there might be a posterior distribution of the parameters.
Exactly.
Yeah.
Exactly. Yeah. Louisa, you have a question?
But is it not more of a frequentist probability, the one that you get? Because really, the actual probability, at least my understanding is that it comes from the number of objects of a certain class in that leaf node. I don't know particularly.
Yeah, so you're thinking about random forests. Yeah.
Right.
So so in the case of random forests, that is the interpretation of that probability. That's exactly how it's calculated.
Okay.
Right? In how many decision trees was this object classified as this? Right? But in the case of a neural network, it's not. It is literally this number. It is tan H of the stuff. Does that mean 80% of the time I would actually call it a cat? I don't know, right? So it's not necessarily a frequentist interpretation in the case of neural networks. In fact, I would say it's probably closer to a Bayesian interpretation because it's, again, conditional on all these things like Brendan said. But it's a point estimate. Yeah. Okay, so it's tea time. And there's been great interaction, which is awesome. So we're taking longer in the lectures, but that's completely fine because we basically got the whole day. Before we go to tea, this is the next question that I'm going to ask you after tea. What is representativeness, and how can your data be non-representative? So think about that at tea time. and we'll come back together in half an hour. Oh, and please, if you haven't tried the notebook, just try it now. Go onto GitHub, download everything, Jupyter Notebook, supernova tutorial.ipynb, and just see if you can run the first cell that's got all the imports. So just make sure everything imports. That's all you need to do. Should take you 2 minutes. And if it doesn't work, at least we'll know that it doesn't work and we can fix it.
Let's make the break 20 minutes.
20 minutes? Okay, we're going to have a 20-minute break. We'll come back at 11:20.